Okay. Yes. So I will give a review on this novel SYK model, which is quite popular in last years, and probably the reason why it is so popular and why does it attract so much attention is because first it is strongly coupled, but despite the fact that it is a strongly coupled model and it is chaotic, we still can exactly solve this model analytically. And this gives us some opportunity to probe the system, to probe strongly correlated systems analytically. And that's probably the main reason why this model is so popular these days. So it has an interesting history. So it started in the condensed matter. So it started by the work of Sachdev and Ye. Ye was a student of Sachdev, and it was it started from so they wanted to study spin liquids, and this model, and then they introduced this model in this context. And later, Kitaev extended this model to high energy. So he proposed a version of this model which can explain black holes. So, and then it started to be more popular in the high energy physics. But then afterwards, it came back to condensed matter, and now it is starting to be popular again in the condensed matter physics. So an interesting fact is that this work by Kitaev, when he generalized this model to black holes, was never published, and actually in many papers that cite the references of the SYK model, they cite this reference of a talk, of a recorded talk by Kitaev in some KITP workshop. Okay, so the outline of this talk, I will first present this model and how we can solve, so I will show how to compute correlation functions in this model analytically. And then I will discuss some applications in solid state, some non-equilibrium behavior of this model, and proposals for experimental realizations of SYK. Okay, so there are several versions of this model. The most popular one, especially in the high energy, is the Majorana SYK. So it is, so this is the Hamiltonian that describes this model. Basically, it has just the interaction term of four Majorana fermions, where there are n Majorana fermions, and they can interact. Each Majorana fermion can interact with any other three Majorana fermions with a random interaction J, where J is averaged to 0, and its variance is constant. Another version is the
yeah. What is large N? Is it the
so
number
there is not many number. So this J, K, L, and M run from 1 to n, and then goes to infinity. So there is a version of this model for fermions, and this is called So the reason why the first version is so popular is because it's real. The Majorana operators are real, and the analysis is much simpler in real operators. And so there is this SYK complex SYK model which describes fermions, and this is obviously more relevant for condensed matter applications. So there are some slight differences due to the fact that it's complex, but the basic features are similar. And there is more general QSYK model, where instead of 4 particle interaction, there are q particle interactions, and these are also are investigated in high energy. So they have some they found some nice expressions when q goes to infinity, but this is less relevant for condensed matter. So intuitive way to understand this model is if we have a quantum dot which has n fermionic states that are strongly interacting. So it's basically a random graph of all-to-all random interactions. And it turns out that this model is solvable in the limit when we take J times the inverse temperature is large, and the number of particles is even larger.
Yeah, I think it's only solvable if you need the interactions to be random as well, the coefficients to be random, right?
So J, yes. So J is the variance of the interaction.
Yeah.
Yeah. Thanks. Okay, so as a warm-up exercise, I want to show the simplest version of the SYK is the SYK2 model, which is actually free fermion Hamiltonian. So so the Hamiltonian has this hopping of fermions with a random hopping coefficient, which is averaged to 0 and has a non-zero variance. And suppose by solving, suppose we want to find the density of states of this model. So one way to solve it would be to find a density to diagonalize this model for many realizations of this Tij, and then find for each realization a density of states, and then average this. So this would be one way possibility to solve this, to find the density of states in this model. And here I want to show a different approach. So we can find the density of states from the Green's function. So the Green's function is the imaginary part of, the density of states is the imaginary part of the Green's function, where the Green's function is defined, where the Green's function is defined as the correlation function between the operator C I dagger at some imaginary time tau and Cj at time 0.
So this bar corresponds to this order average.
Yeah,
right?
exactly. Right. So then we average over this order.
When you say
yeah,
when you say imaginary time tau, what's the initial state?
what do you mean initial state? So we have this model and we evolve it in imaginary time.
Starting from
time equals 0. From the yeah, so you have some finite temperature ground state. So the expectation value is the expectation value here is with respect to some finite temperature state.
You mean Gibbs state
You evolve the
corresponding to
operator?
this
Yeah. So
Hamiltonian?
you have some Gibbs state at finite temperature.
Okay.
So it's an equilibrium and yeah, finite temperature equilibrium state. Okay, so right, so we can find this Green's function using the path integral formulation. So we basically rewrite this as a path integral.
Yeah, I'm sorry. What are the indices I and J?
So there are flavors for these fermions. I goes from 1 to n, and n is large.
And it's not a position coordinate in the
no, so the hopping is there is no position. It's like a zero-dimensional problem. So any particle can hop to any I can hop to any j.
And the density of states has no indices. The imaginary part of G has no I and J. So what do you mean? You sum over I and J?
So it actually turns out that only the diagonal G survives. And it's the same for any I and J.
Okay.
Yeah, sorry, I didn't put it here. Okay, so we can write the Green's function in terms of the path integral. So we integrate over all different trajectories of the fields C and C bar. So these are Grassmanns, and times the exponent of the path integral in the imaginary time. Okay, and then we use the standard Feynman diagram procedure. So we want to expand it in powers of this hopping T, ij. So the Feynman rules would be the free propagator, the one that corresponds to T equals 0, gives us a contribution of 1 over I omega. And if we have a junction, if the term, each junction between I and J gives us a factor of Tij. Okay, and then we can expand.
Yeah. Can I ask a question?
Yeah.
So you wanted to compute the density of states, which was the imaginary part of the Green function at omega equals 0.
Yes.
So it's a number, right? So it's 5. Who cares?
No,
Why
it's
should
not
I care?
omega equals 0. It's as a function of omega. The density of states as a function of omega.
Okay. And what would you like to know? So it's some function. So what is the purpose? What would we like to know?
So the purpose of this exercise is just to show how we can. So this is just a toy model. The SYK2 model is obviously you can solve it in different ways. And so here I just want to show how to find Green's functions, and just as a nice exercise, we can find the density of states.
I think also maybe Ilya, for example, in this SYK model, one of the signatures, one of the special things about it is the behavior of the density of states at small omega.
Which is what? It diverges? What does it do?
No, it's some power law. What is it, square root of omega, Ilya?
Yeah, it goes as 1 over square root of omega.
But
so it diverges like 1 over square root.
Yeah.
Nice. Okay. So this is what one is interested in, the divergence.
That's right. Yeah, that's right.
Okay.
Yeah. So okay. Yes, but this SYK2 model is just a nice exercise where I will show how to analyze this kind of random models. Okay, so we want to find the Green's function, and to find it, we expand it in powers of the hopping T. So the full Green's function equals to the free one, which corresponds to T equals 0, plus the term which has a linear in T term, and then we have the quadratic term, and etc. And at each junction, we put this blue line, and it will correspond to this. So we'll see in a second how are we going to use it. So this is for the disorder averaging. So obviously now, if we want to disorder average this each term, only all the odd terms which have odd number of factors of T will vanish, because the TA is averaged to 0. And then we'll left with only even number of junctions. So now when we disorder average, what we need to do, we need to connect every 2 lines. We need to contract every 2 lines in all the possible ways, and then average over the disorder. So for example, if we take the quadratic in T term, we can only connect the 2 lines in this way. And then the contribution of this diagram would be, so we have T from each of the junctions, and then we have 3 lines, which give us, each line gives us 1 over omega. So now when we average over the disorder, only terms where I equals J survive. And we get a constant from the average. So we get T square over N from from the variance of the hopping, and then we have the contribution from each of the lines. And since this expression is independent on k, the sum over k just gives us a factor of n, and the n cancels with the n from the normalization of the hopping, and we get n independent result. Okay, any questions about this diagram? Okay, so then we proceed to higher order diagrams, and in the t fourth order in the t terms, we have at least three different ways how we can connect these lines. So we can either connect them such that they don't cross, and there is one option where we can have a crossing between the lines. And yeah,
I have a question.
yeah.
Is the hopping Tij is it a Gaussian variable? I mean, do you
so
know about the higher moment something?
Oh yeah, so we're assuming that it only has a second, only has variance. It doesn't have higher cumulants.
Okay, thank you.
Okay, so from the first diagram, we get so the first blue line restricts the possibility for this internal indices to be only the L has to be equal to I. Otherwise, it vanishes under disorder averaging. And from the second blue line, J has to be equal to L, and therefore it also has to be equal to I. And therefore, instead of a sum over K, L, and M, we have only sum over two indices K and M, which gives us a factor of n squared. And this n squared cancels out with n squared, which we get from the normalization, and therefore this term is also n independent. Now, if we go to the second diagram, so here again, the disorder is such that from the outer line, so it connects I, K, and M and J, and I has to be equal to J, and M has to be equal to K. So therefore, M is not independent. And from the second line, the second line actually doesn't restrict any other conditions. So therefore, we also have two independent variables, K and L, and the sum over them gives us n squared. And again, this diagram will contribute to a term which is n independent. However, now if we go to these crossed lines, so here actually the lines are restricting all the indices in the diagram, and therefore we don't have any summation over internal indices, and the contribution of this term would have 1 over n squared suppression. And in the limit when n goes to infinity, this term vanishes, and therefore the cross terms will not contribute to the expansion.
Over n just comes from the way you define the model, right?
1 over, yeah, t squared over n is just a normalization.
It's not, I mean, you define the model such that it has t over n.
Yes.
That's the hopping,
Yeah.
right?
Yeah.
And yeah.
Yeah.
Okay. I mean, the reason why it's reasonable to do that is you want the energy to be extensive. If you divide t over n, the energy, right?
Yeah. So you want in the end you want your result to be n independent.
Yeah. So if I understand correctly, it's kind of defined like that. So the leading order in large n will be independent of n, right?
Yeah. It doesn't matter really. It's just a normalization, but but in the end, you want you want the result to be make sense.
Well, if you haven't divided it by n, you would get a different limit. You wouldn't get this limit. So
No, but still, the crossed line term will be still suppressed by n squared with respect to
that's
the
right.
other
Yeah.
ones.
Mm-hmm. So you're saying the rainbow diagrams, they don't restrict any of the indices. They restrict all of the indices.
The rainbow diagram
Not the rainbow one,
have
the
two
cross,
free parameters. Have two
the
free
crossed ones.
indices, and the crossed ones restrict all the indices, or at least some part of the indices.
Yeah. Mm-hmm.
Yeah. So by the way, the rainbow diagrams called are actually, so this is like the common name for these diagrams that survive.
The Russian days. Yeah. Okay.
Okay. So now when we know that there are no crossings in the diagram, so we can define the self energy as the, so this is like the standard procedure. So we define the self energy as this single particle reducible diagram. So all the diagrams that we cannot divide to two. And then the full Green's function would be a sum of these self energies, which leads to Green's function equals to 1 over I omega plus sigma. And now what would be the sigma? So this sigma would be the full Green's function averaged with this rainbow, which means that it equals to t squared times g. And this is exact in this limit. So this self energy actually includes all possible contractions inside this big rainbow.
So yeah, I'm just confused about the indentation. So the self energy. So the green function is what you denote by this fat arrow, right?
Yeah. So this is the full green function.
Right. And then the self energy is basically adding another two of these interactions on top of this. I mean, and then connecting them by the green function.
Yeah.
Right.
And so it's sort of self-consistent, because this bold line in the cell, this double line in the self energy actually includes the self energy itself. It's already a sum of the self energies.
Yeah, but maybe I mean, I think maybe some people will get lost here. I don't know if somebody else wants to ask a question. So again, maybe I'm just trying to help you explain, or if that, maybe I should ask if other people have a question.
I don't have a question, but I can say something. The way I think about the self energy is you write down the Green's function. It means there's just the free propagator, and then there's the self energy is the part, the sum of all the diagrams that you can't cut in the middle. That's why you need the sum of one of those, two of those, three of those, and so forth. And that's why you get the self-consistent equation at the end of the slide, because necessarily has one. It can't have two rainbows, because then you can cut it in the middle. Two rainbows that different parts that don't cross or aren't nested within each other.
Yeah, that's right.
So and then okay. Mm-hmm. So any other questions? Mm-hmm. Is everybody happy with this? Okay.
The self-energy term, like you go along the line until you reach an arch, and then you go up above the arch till it comes back down, and that's one factor of sigma. And then
yeah, so the one that is shown in the last line.
Yeah, and then under the arch you could have like any number of arches nested in.
Right. So inside this, yeah, this double line represents the sum of the self energies themselves. So it's like you can have one inside the other. It's recursive.
So a sigma means, so again, a sigma means that it's a line that contains only irreducible diagrams, right? You cannot cut it in the middle.
You cannot cut it, yeah.
Yeah. And then you can still have many of those, sum over many of those. I mean, some of a chain of many of these sigmas. That gives you the green function. So that gives you also the equation that G is equal to minus 1 over I omega plus sigma, the geometric series, and also this self-consistent equation at the bottom, right?
Mm-hmm. Okay. So any other questions?
Any other questions here? Okay.
Okay. So then once we get this expression for G as function of sigma and sigma as function of G, we can solve it. So we can plug sigma, the expression for sigma in terms of G inside the expression for G, and we get the following expression for G, which we can solve. So this gives just a quadratic equation for the Green's function, and the solution is this is shown here. Now, this is for real omega, and we can now, if we want to find the density of states, for example, we need to plug in ion. We need to plug instead of omega I omega, and this makes the first term. The first term becomes real, and the second term, the term in the square root, can be either real or imaginary, depending on whether the omega squared over 4t squared is larger or smaller than 1. So if we want to find the density of states, we need to take the imaginary part of this. And therefore, the density of states is non-zero only when omega squared over 4t squared is less than 1. And this gives us this semicircle shape for rho, for the density of states.
Why the imaginary part of G I omega is the density of states?
So this is, yeah, okay. So that's what I told in the beginning. So that's let's say it's the definition of the density of states. It's the imaginary part of the Green's function.
Okay, yeah, right. Sorry, but why I omega?
Oh, you basically, okay. So that's what I told you in the beginning, right?
You're working with imaginary time, right?
So we work with the imaginary.
Right. Okay. Thank you. Sorry for.
And then we want to go to the real frequency, so I need to go to the imaginary axis.
Right. Thanks.
Is there any question with whether you're basically doing a weak rotation here? Whether there's any poles in the middle in the upper half plane or anything, or we're just going to not think about that at all? This model doesn't have it, but maybe there. Forget what I said. Just,
I mean, you see the expression for G.
Yeah.
You can ask if does it.
Yeah, okay. Yeah. Mm-hmm. Yeah. Okay. Mm-hmm. Yeah. This one wouldn't have it. Okay. Mm-hmm.
Okay. So that's the okay. So then we get this semicircle shape for the density of states, and this is actually a null result from random matrix theory, so it's consistent. Okay, so this is the SYK2 model, and now we can do more.
Iliya?
Yeah.
You didn't assume anything about the temperature so far, right?
Right. Yeah. So this is.
I think this is
zero temperature.
Zero temperature. Yeah.
Result. Yeah.
What, did you take beta 2 into infinity here, or was it?
Yeah, that was my question.
Yeah,
I guess since it's free electrons, it doesn't matter. The density of states is independent on this.
that's true. Mhm.
Propagator was for zero temperature, I guess. Maybe it's where it came.
What'd you say, Ari?
Because you use the free propagator.
Right. Yeah, which
Well,
is just 1 over omega.
I see. That's at zero temperature.
Yeah.
Yeah. It's
Wait,
interesting.
no, because I mean omega can be omega can be discrete, and then it would be like finite temperature.
oh, it's the same formula. There's no like exponential. I'm not sure. You would just make a discrete omega instead, and that would give you the finite temperature.
Yeah. Yeah.
Interesting that this calculation gives the same result as random matrix theory.
I mean, it's just a random matrix.
Yeah, but you know, the random matrix didn't have to know about path integrals. Okay, yeah. Mhm.
Okay, so this is the SYK2 model, and now we can do the same procedure for SYK4 model. So now instead of 2 fermion interactions, we have 4 fermion interaction, which is still random, and the vertex here has 4 legs, connects 4 different fermions, and we add this blue line for the disorder averaging.
So we're again assuming this zero temperature thing here. I mean,
here in the SYK4, you are asking about the SYK4. So here we'll assume finite temperature here.
Ilya, what's the meaning of the arrows in these diagrams now? Because you're doing the Majorana version, right? So is there any meaning to the direction of the arrows?
I think there is no actually meaning. Yeah, well, there is a meaning. There is a minus sign that if you
You have to keep track of the order, right?
What?
You have to keep track of the order.
Yeah, so you need the order because of the minus signs.
Okay, so how does the order? I see. So, but is the order somehow tracked by the direction of the arrows somehow? I see. Okay, I guess it maybe, yeah.
Yeah, it somehow it should matter.
Okay.
Okay, so now we expand. Our Green's function should be expanded in these 4 fermionic terms, and I already throw away the odd in J terms, since they will be averaged to 0. So here we have this kind of bubble diagrams. So the 0th order is just the free propagator. Then the 1st order would be this 1 bubble, and then we can have 2 bubbles in a row, or we can have 1 bubble, and then there would be 1 small bubble inside this one. And we can also have a crossing between the bubbles, in principle. However, we'll see now that the crossing, if we have the diagrams which have crossing of the bubbles, they will actually average to 0 in the large n limit.
Yeah. Right. This is what you call a crossing. Okay. Yeah. Mm-hmm. Yeah. Okay. Yeah. Mm-hmm.
Yeah. So let's see how it works. So let's examine this diagram with crossings between the bubbles. So let's say that we take we contract the disorder averaging in this way, in the way that is shown in the figure, and let's instead of indices, I put numbers. So I just call 1 to 9 the different flavors of the fermions. So the first rainbow that connects, the one that is to the left, So it requires that the index 1 has to be equal to the index 6, and the index 3 has to be equal to index 5, and 4 to 7. And from the second rainbow, 5 has to be equal to 6, and 3 to 9, and 4 to 7. And in the end, instead of, so initially we need to sum over all the indices 2 to 8.
Yeah.
But now there are some dependent indices, and therefore, so there are actually just 3 independent indices left, 2, 8, and 4, for example. And therefore, we get a factor of n to the third power from the sum. And there is a factor of j to the 4 divided by n to the 6 from the 4 couplings. So then in total, we get that the contribution goes as j to the 4 divided by n to the third. Oops.
Wait, so can you just show that? So you're saying, if I look at this diagram, you wrote 2 possible options. 1 is equal to 6. That's 2 solutions. 1 is equal to 6 to...
No, so in principle, so for this option of the contraction of the rainbows, 1 has to be equal to 6. So you need to take, so the index that enters the first vertex has to be equal to index that goes out of the second vertex. So then if 1 enters the first vertex, then 6, which goes out of the second vertex, has to be equal to 1.
How do I see that? Can you help me?
This is because you need to have the same indices for j of the first vertex and j of the second vertex.
So you mean otherwise they shall vanish.
So why can't 1 be equal to 2?
Yeah, one can, there is another option when 1 equals to 2. Yeah. Right. This would be more restrictive.
The one is the first J is J1. J1. I don't know. Remember what the order was.
J1, 2, 3, 4. Let's say.
Yeah.
And the second one is J 5,
6, 7, 8.
7. No, J 5, 7, 2, 6. 5,
7, 2, 6. That's right. I see. I 7, 5. I see. And the 6. That's why you're saying 6 is equal to 1.
Yeah. You can also exchange the orders, so then you have another option. But
because you're treating each one of these matrix elements, each one of those tensor elements as a random variable.
Yeah.
I see. Okay. Yeah.
Okay. Any other questions on this? Okay. So then this cross diagram will be suppressed by a factor of n to the power of 3. And just for comparison, let's see what happens for the one which is not crossed. So then here the only restriction from the contraction would be that 5 has to be equal to 1 and 9. And therefore, we have a summation over 6 internal legs. And this gives us a factor of n to the power of 6, and which cancels with the normalization, and we get a constant in n term. Okay.
Yeah. So as long as they don't cross. So what about that thing that had the bubble on the top? Diagram that had the bubble on the top. That's also fine.
The one which is here.
Left. Yeah.
Yeah. So this is allowed. As long as you don't have this kind of crossings, the diagram is allowed.
Okay. Yeah.
Yeah.
Can you also have things where the bubbles cross and they actually have an interaction at the point where they cross?
What do you mean? Yeah.
Because they're like, they're just like four, like the vertices have just four lines coming out of them.
Yeah.
All the things you drew seem more like specific, like having one line with a bubble going across it, but it seems like two bubbles could just like at that intersection point, it could actually have a vertex there.
I see. So you're saying that intersection point could be a vertex itself, but that would be high order, no?
Yeah, I mean, if you wanted when you get to higher order, maybe it only.
You asked, for
Yes,
example,
is that it would be also suppressed because it's quite restricted.
okay. So what is the claim? Which diagrams survive?
So the claim is that the diagrams that survive are the ones that do not have crossings.
So only these type of diagrams? I see.
Yeah. So this is the example. So the figure so this figure, which has a lot of bubbles, this is a typical example for a diagram that is allowed. Okay. So you can have any number of internal bubbles. Okay, so then we can, since we don't have crossings, we can again define the self energy, which in this case would be would have this form of a bubble, where each line is actually the full Green's function. So this covers for all the options for all the possibilities of this recursive, this bubble inside bubble. Okay, and then from these two diagrams, so from the first diagram, we know that the Green's function goes as 1 over I omega minus the self energy, and from the second diagram, we find that the self energy should be proportional to the full Green's function to the third power times j squared. Okay, any questions? So it looks like the result is very similar to what we got for SYK2 model, and looks like we can also solve it analytically or in the computer. But there is one caveat. Actually, these equations are not so simple because they are defined in different domain. So the Green's function, the first line is defined in the time domain, while the second line is defined in the frequency domain. Do you have questions?
Why did this not happen before?
Yeah, so before we had just one line for the self energy, right? And then it doesn't matter. You can define it in any, you can define it in the frequency space or in the time domain. But when you have 3 lines, like here, each junction has the same time, but it has a, so if you do it in the time domain, each vertex corresponds to a different time.
Yeah. The shorter answer is before the equation, the first equation was linear, so then you can just Fourier transform it, no problem. But once it becomes nonlinear, then
right.
Then you cannot just put omega instead of tau.
Yeah, and actually, this kind of diagram looks more nicely in the time domain. It just looks like sigma equals to Green's function to the third power. But if we transform this to the frequency domain, this has some integral equation. So you need to sum over sum of the frequencies of the legs, of the free legs that we have, of the internal legs that we have in the diagram, right? So each vertex conserves the energy. So you have the energy conservation of each vertex, but the energy of each line doesn't have to be, it can be anything. You need to integrate over the energies of each line.
A question, I mean, maybe a more broad question. Looking at the structure of what you've done, would things have been very, very different if instead of starting with a model of fermions, you had started with a model of bosons? I don't see something terribly.
So you mean replace the fermions with bosons?
Yeah, for four bosons interacting, and yeah, I guess I just don't see, like, it seems like the structure would be pretty similar, because you've just used the fact of the contractions, that the diagrams that don't that survive the averaging are just the ones. It just has to do with the indices having to be as different as they can be from each other, but that had nothing to do with them being fermions. And so no, anyways, I just wonder. It's a
so I know at least about one work by Ares, actually, which was published recently, where they discussed SYK model for bosons.
Okay.
And actually, so there they can take 3 boson interactions. They don't need to take 4 boson interactions.
Right.
But they still need to add somehow the 4-order term to conserve energy, because otherwise, because the interactions get so somehow they have problems with energy conservation. They have just if they have just 3 boson model. So so there are works that are.
I see. Okay. Yeah.
There's also an old work by Subir about the spin SYK model. And I think there is something different there. There is some qualitative difference. I don't remember what it is.
Okay.
Since it's random coefficients, it would be hard to make sure it doesn't get like an infinitely negative ground state energy, I would think, for bosons.
I see.
Yeah, right. Yeah, that's why they had some force order correction terms. Okay, so yeah, so these equations are not easy to solve, at least analytically. And the trick that people are using, they neglect this I omega in the denominator. So then the Green's function is approximately equal to 1 over the self-energy. So this is true. This approximation is valid when beta times j is much greater than 1. So when omega is of the order of temperature and sigma is of the order of j. So as far as sigma is greater than omega, this approximation is valid. Okay, and once we do that, now the equations get some nice form. So they actually scale invariant. So we can rescale sigma in G, and the solution will not change. And this suggests that we have some conformal symmetry here, and the solution would be some power law. So to solve these equations, we use these ansatz of the power. So the Green's function goes as 1 over tau to some power 2 delta. And from the first equation, it means that the self-energy sigma would be the third power of G. So it would go as 1 over tau to the power of 6 delta. And if we Fourier transform this to the frequency domain, then we get just from some identities of the Fourier transform that the Green's function of omega goes as omega to the power of 2 delta minus 1. And if we Fourier transform the expression for the self-energy, we get that it goes as omega to the power of 6 delta minus 1. And then from the second equation, we can find a relation from the consistency between the solutions. We can find a result for delta, which turns out to be 1/4.
What's the reason for choosing these ansatz? How do you know that you have to choose a power law?
So the reason is because you see that the equations are scale independent, so you can rescale sigma and g.
Mm-hmm.
And that's why you're guessing that it should be some power law solution.
Mm-hmm. Okay.
Right, so then you get delta equals 1/4, and this means that the Green's function would go as 1/square root of tau, or 1/square root of omega, and the self-energy goes 1/tau to the power of 3/2, and self-energy in the frequency domain goes the square root of omega. So now we can go back to the approximation that we did and compare whether this approximation is good. So we throw away omega, factor of omega, with respect to sigma. And it's actually a good approximation because at low frequency, square root of omega becomes larger than omega. And this is also one of the indications that the system does not have quasi-particles, because we throw away this omega, so the Green's function does not have simple poles anymore. And yeah, and instead it goes as 1/square root of omega. And yeah, and now we can also draw this Green's function, and looks and has this divergence of 1/square root of omega. Any questions about the model?
Okay, so what do we do with this?
Okay, yeah. So that's that was the first part, basically, the longer part where I showed how to analyze this model, and now I want to shortly discuss the applications of this in condensed matter.
Ilya, so yeah, just we take a break, or do you want to go? How long do you have to go?
I think it won't be too long. Maybe like 20 minutes.
Okay, so continue.
And if not, if I want to get to the end, we can cut it at any point, because like the last part is less important. Okay. So right, so I wanted to show how this is used in condensed matter and solid state, and the most important result is that it can describe linear T resistivity in strange metals. So there are some materials that show, yes, sorry. So usually metals have a quadratic. The resistivity of metals goes as quadratic with the temperature. So this is the standard result from the Fermi liquids. So we can find the resistivity from the Drude formula, which is inversely proportional to the scattering time, and the scattering rate from the Fermi golden rule, for example, will go quadratic. Will be quadratic in the temperature, and that's basically because the fermions, the electrons scatter in relaxation processes that contribute to the resistivity are residing near the Fermi surface, and that's the reason for quadratic in the temperature result. However, there are some materials that do not behave according to this formula, so they have a linear resistivity as a function of temperature. So these are some plots from some cuprates, which show this linear interior resistivity, and these are called the strange metals. And there is no good theory that can explain this linear resistivity in temperature. And it looks like this SYK model can explain this to some extent. So the basic SYK model describes a zero-dimensional problem. And the way to extend it, the way people extend it to higher dimensional systems is by creating a lattice of these SYK models where where the model basically has many SYK dots, and the particle electrons can hop between the dots with some hopping coefficient T, or they can interact with other electrons in this dot with the coefficient U. Okay, so that's the model. And you can compute the conductivity for this model. So the conductivity would be some expression in terms of the Green's functions. So A here is basically the density of states, the Green's function. And it turns out that the conductivity, the resistance as a function of temperature has this linear dependence on the temperature. However, at very low temperatures, it still becomes quadratic. And the crossover between the quadratic dependence and the linear dependence is called coherence energy. So it goes as T squared over U, so it has to be U. And the reason why it becomes quadratic is, this is some property of this SYK model, is that if we add, so essentially the model itself has the interaction term and has hopping, and at very low temperatures, so the property of this SYK model is that at low temperatures, the interaction term, the 4 fermion term, becomes irrelevant, and therefore at some point the quadratic term becomes more relevant than the interaction one, and therefore at some point you get the system becomes a Fermi liquid again. Any questions?
It becomes a Fermi liquid at low energies, at low temperatures.
Yeah, just because. So you can see this from. Yeah, you can see this from the Green's function. So we have the self energy, which goes as square root of omega, and if we add some constant term to the denominator of the Green's function, it will dominate. It will dominate over the self energy.
Okay.
Okay. Yeah.
Each of these dots is highly disordered, right? You have a
right. So there is disorder inside the dots.
So you should get a residual resistivity at 0 temperature.
Because you have finite entropy.
You should get what?
Because you have finite entropy at 0 temperature, you mean?
No, not entropy. Just disorder. You have impurities. You're scattering.
But it's not a scalar. It's not a potential disorder. It's only a disorder in the interaction.
Some parts of it, if you take expectation value on C dagger C, you get a potential disorder, which scatters from beta to delta, let's say. You cannot have blockways, I think. Do they get the saturation at low temperatures, or they just get it go to 0 with temperature?
Yeah, that's.
I see that there is a saturation in the figure you drew, but maybe that's.
But I think that you are right, because, yeah. So I don't know the answer. I need to read more carefully this work, but the reason probably that's the reason why they call this phase an incoherent metal. Exactly because
So it's a metal with a strong disorder, right? It's not going to be a clean metal model.
Yeah.
Okay.
Yeah. Mm-hmm.
Okay.
Right. So
Wait, what they call an incoherent metal is the thing that goes as T, not as T squared. Right? What they call it?
Yeah, the incoherent. Yeah, I'm not sure actually.
No, I think they mean T squared is a sign of Fermi liquid, so
yeah,
they want it to be like a Fermi liquid, and T is non-Fermi liquid. Whatever.
Yeah. Yeah, I'm not sure about this. Yeah, so,
Okay.
so this linear and T part usually it's called Planckian metal.
Oish. Okay.
Okay. Yeah, so that's all I wanted to tell about these lattice models, and there are other interesting works. So there is one work that shows that you can get superconducting instability from these SYK interactions with no need of attractive interactions from phonons. And so this is related to what Daniel asked. So there is this recent work which tries to explain some anomalous thermal conductivity by looking at bosonic SYK model for phonons. Yeah, and then some another work which is related to condensed matter, but is from a bit different field, is the one where you can actually observe a phase transition from some chaotic system to a localized one, and so this work. So in this work, basically, the authors take disordered electrons with no interactions and electrons with SYK interactions, and they couple them. And as a function of this coupling between the two different flavors, you can get either a localized phase or a delocalized phase, and you can actually access the phase transition analytically. Right. Okay. So now I want to. So these are nice applications of this SYK model to show some results of the in the condensed matter physics. And now I want briefly to review some works that realize SYK models using condensed matter setups. So this is so-called black hole on a chip, and because the point is to model the physics of a black hole, which is described by this SYK model. You model this black hole using some condensed matter device. So there are some works that try to model this SYK using Majorana particles. So so this is a figure from one of these works, which shows a setup, basically, which tries to model a P plus Px plus IPY superconductor, which has Majoranas, which has Majoranas in the vortices, and then they add a magnetic field which is random, which creates vortices, which creates Majoranas with random wave functions. And the idea is that these Majoranas, if they are close enough, they will interact, and this interaction can be described by this SYK model. Okay, so what is shown here is this device, and it is floating in the space, and there is to the left there is a black hole. So this is a figure from the paper where it was proposed. And another proposal considers, so another proposal is for CSYK, for a SYK model with fermions, which can be realized in a graphene flake. So there, they suggest that we can get rid of the kinetic term by applying a magnetic field, which makes the band flat. Okay, so they suggest to work in the zeroth Landau level where I have electrons and holes that can interact. And the randomness of this model would be realized by boundaries of this flake, which would be random. And this will create random wave functions. But so the wave functions would be random, but the band would be still flat. And therefore, the interaction, the local interaction, which is the expectation value that's written here, would be random. So they studied this J, and they show that it can be actually it becomes Gaussian with zero average, with zero expectation value. And the claim is that you can realize this SYK model in this setup. Okay, any questions on this part?
How many, how many interacting whatever fermions can you get in the flake? Because if the flake is too big, then you don't enjoy the randomness. The randomness becomes not important, I guess. The randomness is only from the boundary, right?
The randomness is from the boundary. That's right. Yeah.
If it's too big somehow, then you don't.
Yeah, you also that's right. You want to be probably the flake shouldn't be too large.
This is the work by Marcel.
Yeah.
Okay.
Here, the number of modes, this IJKL, that's supposed to be, I mean, that's basically where do those modes live? They're like lattice or?
No, I think they're just modes of this flake, eigenmodes of this flake.
Yeah. But eigenmodes means but meaning you have as many of them as lattice basically.
No, it's in the zeroth Landau level, so
okay, fine. Yeah. Okay.
The number.
Okay, so it's like the number of it's a number of fluxes in the in the flake. Okay.
Okay, so these are the realizations, and probably I'll skip the out of equilibrium SYK models because it is more related to what I'm doing with this model, but maybe it's less interesting.
With drive or with some time dependence?
So there are several proposals. So there is a quantum quench on the model. That this was the first work in this field, and then there is periodically driven SYKs, and there is even a temperature quench. Light.
This is what you showed me, the wormhole.
Yeah. So in the language of high energy, this SYK is a black hole, and if you have two coupled SYK dots, it is like a wormhole between two black holes.
Okay. How much this analogy can be pushed, but the only relation to okay, I don't know if the only one, but the relation to black holes is the claim that it's kind of maximally thermalizing in some sense. It's right. So it somehow saturates the Senna bound for for thermalization, which we did not discuss here.
I did not discuss it, but yeah. So there is one of the important properties of this model that it it thermalizes very quickly. Yeah, it saturates the bound for the.
There's a bound by Maldacena for how fast the system can thermalize, and apparently this model saturates the bound, right?
Yeah, in some limit it saturates the bound when the interactions are strong enough. Beta J is large.
Okay.
Yeah, so I guess, yeah, so there are also other applications in high energy, which I won't touch.
Yeah, how does a zero-dimensional model relate to anything in higher dimensions? That's something I don't understand.
So you mean this, the lattice SYK models?
No, the lattice is trying to make it related to something, but I'm saying about the pure SYK is a zero-dimensional model.
Yeah.
And they want to relate it to like an extended field theory, right? Or to some, well, in gravity, I mean, they live in higher dimension than zero, right? I mean, usually the mapping of gravity is to some conformal field theory in 3 dimensions or something, not 0 dimension. I have not understood the fascination with the 0 dimension.
So this is related to holography, right?
Right.
ADS CFT and the fact that the SYK is the CFT, and it describes ADS2 gravity, which is 2-dimensional actually.
Well, especially when they're discussing transport and thermalization, it depends on which dimension you are, right? Or you have modes that carry heat. So what does it all mean in terms of?
Yeah. Yeah, I have no answer.
Yeah, or you can say it's an infinite dimensional model if you think about every one of these degrees of freedom is essentially tied to everything else. So that's like being in a hyperlattice of infinite dimensions. But I want to know how they relate whatever properties this model has to anything extended. But for that, I need to listen to string theorists, which I have no patience for. Okay.
Yeah. Okay. So any more questions? Okay, so then I guess that's it.
Thanks.
Okay, thank you very much.
Thanks for.
Thank you.
Thank you. Thank you very much.
So next week we'll have a group meeting by Tasnim. Okay.
Very good.
Okay.
Yeah, bye.
Bye then.
Bye.
Bye.
Bye. Bye.
Bye.
Bye.